What if I told you that astronauts age slower than us on Earth? It sounds like science fiction, but it's a fact. It's one of the mind-bending consequences of Einstein's theory of relativity. Time, as we experience it, is not a constant. It's relative. Imagine identical twins. One stays on Earth, the other journeys into space at incredibly high speeds. When the spacefaring twin returns, something remarkable happens. They are younger than their Earthbound sibling. This isn't just a theory, it's been observed. Atomic clocks accurate to a fraction of a second have proven that time slows down at high velocities. The faster you travel, the slower time passes for you relative to someone standing still. This phenomenon, known as time dilation, is not just a scientific curiosity. It has profound implications for our understanding of the universe and the future of space travel. Before Einstein, we thought time was like a river, flowing at the same rate for everyone. But Einstein shattered this notion. He showed that time is more like a dance floor, where your experience of time depends on your movement. His theory of relativity revolutionized physics. It revealed that space and time are intertwined, forming a four-dimensional fabric called spacetime. Massive objects warp this fabric, like a bowling ball on a trampoline, creating what we experience as gravity. Time dilation is a direct consequence of this interconnectedness. As an object approaches the speed of light, its motion through space increases, while its motion through time slows down. This is to preserve the cosmic speed limit, the speed of light, which is constant for all observers. Imagine a photon, a particle of light zipping through the cosmos. It travels at the ultimate speed limit, approximately 299,792,458 meters per second. Nothing in the universe can travel faster. But this speed limit has a strange consequence. It forces time to warp. Einstein's special theory of relativity tells us that the laws of physics are the same for all observers in uniform motion. This means that no matter how fast you're moving, the speed of light will always appear the same to you. So if the speed of light is constant and you're traveling at a significant fraction of that speed, something has to give. That something is time. Time slows down to compensate, ensuring that the speed of light remains constant from your perspective. This is why the traveling twin ages slower. Their time has slowed down relative to their Earthbound sibling because they are moving at a significant fraction of the speed of light. The concept of time dilation might seem bizarre, but it's grounded in a simple yet powerful equation. This equation, derived from special relativity, allows us to calculate the extent of time dilation. dt equals dt divided by the square root of 1 minus v squared over c squared. Don't let the symbols scare you. Let's break it down. dt is the time interval measured by the moving observer, the astronaut. dt is the time interval measured by the stationary observer, on Earth. V is the velocity of the moving observer relative to the stationary observer, and c is the speed of light. This equation tells us that as the velocity of the moving object approaches the speed of light, the denominator of the equation approaches zero. As a result, the time interval experienced by the moving observer becomes smaller compared to the time experienced by the stationary observer. Time dilation is not just a theoretical concept, it has real-world implications. For example, GPS satellites orbiting Earth at high speeds experience time slightly slower than we do on the ground. To maintain accuracy, their clocks are adjusted to compensate for this difference. In the realm of particle physics, muons, subatomic particles created in the upper atmosphere, provide further evidence of time dilation. Muons have a short lifespan, but they travel at nearly the speed of light. Because of time dilation, they live long enough to reach the Earth's surface where we can detect them. One of the most compelling examples of time dilation involves Russian cosmonaut Sergei Krikalev. He spent over 803 days in orbit aboard the International Space Station, traveling at speeds of around 17,500 miles per hour. Due to time dilation, Krikalev actually aged about 0.02 seconds less than people on Earth, a small but measurable difference. One of the most intriguing thought experiments related to time dilation is the twin paradox. Imagine two identical twins. One stays on Earth while the other embarks on a journey through space at near light speeds. According to the theory of relativity, the traveling twin would age more slowly than the one who remains on Earth. Upon returning, the spacefaring twin would be significantly younger than their Earthbound sibling. This paradox challenges our intuitive understanding of time and pushes us to reconsider the very nature of reality. In 1971, an experiment known as the Haffel-Keating experiment brought the twin paradox closer to reality. 4 atomic clocks were flown around the world on commercial airliners, while another set remained stationary on the ground. When compared after the flights, the airborne clocks showed a slight discrepancy, having experienced time slower than the ground-based clocks, just as predicted by relativity. These real-world demonstrations reinforce the mind-bending consequences of traveling at relativistic speeds. As we continue to push the boundaries of space travel, the twin paradox serves as a fascinating reminder of how much we have yet to learn about the fabric of the universe. Would you volunteer for such a journey, knowing you might return to a future Earth far different from the one you left behind? If you liked this video, don't forget to subscribe to our channel. If you could travel at near light speed and experience time dilation, would you do it? Let us know in the comments below. Time dilation opens up tantalizing possibilities for space exploration. If we could achieve speeds even closer to the speed of light, we could potentially travel vast distances across the cosmos, experiencing significantly less time than those back on Earth. Imagine traveling to a star system thousands of light years away, and returning to Earth centuries in the future, having aged only a few years. The movie Interstellar beautifully illustrates the concept of time dilation near a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. The protagonist and his crew land on a planet orbiting a supermassive black hole. Due to the intense gravitational field, time on the planet flows significantly slower than on Earth. For every hour spent on the surface, 7 years pass on Earth. While we haven't cracked the code of interstellar travel or built spaceships that can approach the speed of light, time dilation remains a fascinating area of study. It pushes the boundaries of our understanding of the universe and hints at a future where humanity might one day unlock the secrets of time itself.